We're going to take a look at the characteristics of polynomial functions in this video. So before we get into those properties of those functions, we should talk about what a polynomial function is. So I've given some examples of some polynomial functions. Here's one here, f of x equals x squared minus 5x plus 3. Here's another one, f of x equals 2x plus 4, f of x equals 5x to the power 6 plus, or minus 3x cubed plus 4x. So these functions here all have one variable, in this case x, and the exponents on those variables are whole numbers. So in other words, the exponents are either 0, 1, 2, 3, 4, 5, 6, so on and so forth. So polynomial functions have to have exponents on the variable that are whole numbers. So these would be some non-examples. This function here has an exponent of 1/2. Well, you can't have fractional exponents on x for it to be a polynomial function. Another way of writing that one there would be the square root of x, because remember the denominator of this exponent represents our root. So f of x equals root x. In the second example here, we've got another problem. It kind of looks initially like, well, hey, they're all exponents with whole numbers on them. But remember, this one here, this divided by x to the 4, is really the same thing as saying x to the minus 4. And we can't have negative exponents. That's not a whole number. So that's another non-example. There can be no exponents of x in the denominator. So a polynomial function will have this basic property to it. Some number x to the power n, maybe another coefficient x to the power of n minus 1, and there might be a whole pile of other terms in here, and then there would be maybe an x term and a constant term at the end. So these a, b's, c's, and d's, those are the coefficients. They can be whatever you want them to be, but the important part is that the exponent n has to be a whole number. So n is an element of the whole number set. It's got to be a number like 0 or 1 or 2 or 3 or so on. So let's look at some graphs. Let's start with a polynomial function that's of degree 0. And when we mean the degree of the polynomial, we mean what is the highest exponent that's in the polynomial function. So the simplest case here might be the graph f of x equals 4. And really that's like 4 times x to the power of 0, because x to the power of 0 would just be 1. Remember, anything to the power of 0 is 1. So this is why we would call this degree 0. And you remember that a line y equals 4 is a horizontal line right up here where y equals 4. So for a degree 0, we basically get a horizontal line, and this graph's going to go to the left forever and to the right forever, so we can say the domain is all real numbers. And in this case, the range is just one number, y equals. Let's see what happens when we start to put a degree of 1. So now we can put a 1 on the exponent of x. So this might look like this. Say 2x minus 1 as an example. Well, you should remember this from a previous math course. This would have a y-intercept of minus 1 and a slope of 2. So we might have a graph that looks something like this. And so a function of degree 1 will be a line like this, or it could go this way. These are all examples of degree 1s. But the domain of this graph will be all real numbers because it goes to the left and to the right forever. And the range of these functions will be y all real numbers as well. It goes down forever, it goes up forever. So you've seen those before. You've worked with those polynomial functions, and you've also worked with these polynomial functions. Degree 2. This is our parabola, and it might look like this. Say 2x squared minus 3. And if we were to sketch a graph of that one, it would look something like this. And so here we can say the domain is all real numbers, but the range, because it goes to the left and to the right forever, but in this case the range is going to end up being y values greater than or equal to negative 3, because that's where this point would be right here. This is the point 0, minus 3. So I like to think of it so far this way. Degree 0 is kind of a unique thing. It's just a horizontal line. But when we have degree 1, there's sort of one part to the graph. Degree 2 has almost two parts to the graph. There's the part that comes down here and the part that goes back up this way. Let's look at some other degree functions. So a degree 3 is going to have 1, 2, 3 parts to it. That was annoying. Go away. Yeah. 1, 2, 3 parts to it. And it would look something like that. And a degree 4 might look something like this. 1, 2, 3, 4. And a degree 5 might look something like this. 1, 2, 3, 4, 5. Might have 5 parts to it. And so with the degree 3, we might have, for an example, not that this graph will look like this equation, but as an example, this would be a degree 3 function. 2x cubed minus 5x squared plus 7x plus 3. And a degree 4 would have maybe 5x to the power 4, and then there might be some other parts to it here too, maybe a cube. Maybe there's 0x squared, but there's minus 7x plus 4. And a degree 5 would need an exponent of 5 as its highest power. And maybe there's a bunch of other stuff in here too. There's an example of a degree 5 equation. Again, these equations here will not necessarily match with the graphs I've drawn, but this would be an example of an equation that's degree 4. Now, so let's go back and look at its other properties. What is the domain of this function? Well, all real numbers. What is the range of this function? Well, it goes down forever and it goes up forever. So all real numbers. How about this one? Domain. All real numbers. To the left forever, to the right forever. But here, the range might be y greater than or equal to, let's say this is the low point here, and let's say that this is a y value of negative 4. I'm just making that up. Here, we would say y is greater than or equal to this value here. Then we go back and look at this one, degree 5, all real numbers. Y, all real numbers. Whoops, range. Y, all real numbers. So there's a bit of a pattern here, and maybe you've figured that out. If we go back and look at these ones, degree 1, when the exponent or the degree was odd, we seem to have a range that was all real numbers. So degree 1 was all real numbers. Degree 3, range all real numbers. Degree 5, range was all real numbers. But when we look at the even ones, like the parabola here, we have a range where y is greater than or equal to a certain number. And same thing here. The degree 4, let's get her down there, y is greater than or equal to a certain number. And in all cases, in a polynomial function, the domain is all real numbers. So, domain is always all real numbers. If the degree is odd, the range will be all real numbers. And if the degree is even, the range might be y greater than or equal to something, or we'll look in a bit and see that it might be y is less than or equal to something. But in other words, the range is not all real numbers. So let's review what we've learned so far about polynomials. We know that the degree of the polynomial is equal to the highest power of the exponent. we know that a degree 1 will have sort of one part to the graph, a degree 2 will have 2 sections, 3 sections, 4 sections, 5 sections. And we've learned that when the degree is odd, the range will be all real numbers, and when the degree is even, the range will not be all real numbers. There'll either be a minimum point, or we'll look in a bit, maybe a maximum point. And in all cases, the domain is all real numbers. The other thing we can notice from this is that the degree of the polynomial is always going to give you the maximum number of roots. Now remember, the roots are where it crosses the x-axis. So this is degree 1. It has possibly one x-intercept. This is degree 2. It has at most 2 x-intercepts. Degree 3, at most 1, 2, 3. Degree 4, possibly 4. Degree 5, possibly 5. Now this number here in front of the x cubed, we call the leading coefficient. It's called the leading coefficient because when we write it with the largest power first, this would be the leading coefficient, the first number that we see in front of the variable when we write it in descending order. So I've got two cubic functions here, and in this case the leading coefficient is positive, and in this case here the leading coefficient is negative. And this has a tremendous impact on our function as well. So we know this is a cubic function. So a cubic function is going to have sort of these three parts to it. It might look something like this. Again, I'm just showing you what a graph like this might look like. This equation here is not necessarily going to be this graph, but it'll look something like this. It's going to have three parts to the function. If the leading coefficient is positive, then this on the far right-hand side is going to be positive as well. They call this in the book the end behavior. So when we have a positive leading coefficient, when you look at what happens when x gets really, really large, in other words, if we go to the right forever on this graph, the graph will end up going towards the positive y values. This one has a negative leading coefficient, so this means it's going to go down when we go to the right. So when we go way over to the right in this function, it's going to be going down. And then we still got to have sort of that three parts to the function. So it would look something like this. So the leading coefficient is positive, it's going to move up to the right. If the leading coefficient is negative, it's going to go down to the right. So that's another characteristic of a polynomial function. The leading coefficient tells us what the graph is going to do, which direction it's going to go when we move as far as we can to the right in the function. So without knowing at all what this graph would look like, let's see if I can tell some of the characteristics of this function. Well, I could be asked, what is the degree of this function? Well, I'm going to search for the highest power. There it is. It's of degree 4. This means it's going to have 4 parts to the graph. I could also be asked, what's the maximum number of x-intercepts? The maximum number of x-intercepts will also be 4. I could be asked what the domain's going to be. Well, the domain of all polynomial functions is all real numbers. I could be asked what the range of this function is, and let's leave that one for a second because the other thing we're going to look at now is, what does the leading coefficient tell us? Well, the leading coefficient here is negative, so this means that the end behavior is that it's going to go down to the right. So this is enough information now for me to do a very rough sketch of what this graph might look like. So I know it's going to go down to the right, so I'm going to draw an arrow going down to the right, and then it needs to have 4 parts. So it might look something like this then. I know it had to go down to the right, and 1, 2, 3, 4, because it was a degree 4. Here I've shown that there's a maximum number of x-intercepts of 4, and I have them here. But I wouldn't have to necessarily even draw it that way. I could draw it like this. I could draw it so that the graph does this. Now there's actually only 2 x-intercepts, because it's doing a squiggle here above the x-axis. Or I could even draw it like this. And here there's no x-intercepts because it's doing its function below the x-axis. We'd have to actually put that in the graphing calculator or do a table of values to actually see what that graph looks like. But this would be an example of a graph that would have some of these characteristics. It's negative, so it's going down to the right. It's got 1, 2, 3, 4 parts to the graph, so it's a degree 4 graph. And its range now, I don't know what the range of this function is, but it's not going to be all real numbers. It's going to be y less than or equal to whatever this highest value here is, which let's just make this up. Let's say that's a y value of -2. So we can say the range is y less than or equal to -2. So we can tell a lot about what the graph will look like just by looking at the polynomial function. Now there's something else we can very quickly tell by looking at a polynomial function, and that is the y-intercept. Remember, the y-intercept is where the graph crosses the y-axis. This is our y-axis here. And all of these places along the y-axis has an x value of 0. X equals 0 at this point right here. So if we want to find what the y-intercept is, to find the y-intercept, just make x equal to 0. And in a polynomial function written like this, when you put 0 in for x, 0 to the power 4 is 0. 0 times -2 is 0, so that's 0. This term becomes 0. This term becomes 0. And so when it's written in this form here, the y-intercept will always just be your constant term, because that's what you would get when you put 0 in for x. So the y-intercept of this function would be 4. And so that's another indicator here that my graph wouldn't be quite right. It should have a y-intercept of 4, so it should be going through this point right here. Let's look at another example here. Let's see if we can find out all of this information for this function here. 5x cubed minus 2x squared plus 7x minus 1. So we have a polynomial function here. And what is the degree? Well, we'll look for the highest exponent there, which is 3. The maximum numbers of x-intercepts is always equal to the degree, so there could be at most 3 solutions here. The y-intercept, well, that's just our constant term, because when we put 0 in for x, those all disappear, and we would have f of x equal to -1. So our y-intercept's -1. The domain, well, this is a polynomial function, and all polynomial functions have domains of all real numbers, so XER. The range of this function is all real numbers as well, because it's an odd, has an odd degree. So when there's an odd degree, the range will be all real numbers. And the end behavior, here I'm going to look at the leading coefficient. It's positive, so it's going to go up to the right. So we might have a situation like this, going up to the right. It's going to have a y-intercept of -1. So I could even do something like that there. Let's see, degree 3, 1, 2, 3. Y-intercept of -1, sure, it's going through -1. Domains all real numbers to left and right. Range is all real numbers up and down. forever, and the end behavior is going up to the right. So there's an example of what that sketch might look like. And so you should be able to, given a polynomial function, you should be able to find out what these properties of that polynomial function are and give it a sketch which would show the general shape of what it will look like.